Here's how you can use conservation of energy to predict how fast something will be moving if it rolls from rest down a ramp without slipping. As usual, we're going to start with conservation of energy. The mechanical energy at the top of the ramp is equal to the mechanical energy at the bottom of the ramp. And this is true because when something rolls, there's very little friction to sap energy from the system. The work done by friction, the non-conservative work done by friction, is essentially zero. So at the top of the ramp, the object's energy is all gravitational potential energy. And at the bottom of the ramp, the object's energy is all kinetic energy. But when an object rolls, part of the kinetic energy is the usual translational kinetic energy because the object is moving. But part of the kinetic energy is tied up in the object's rotation. That's the kinetic energy of rotation. So the translational kinetic energy is the usual 1/2 mv squared. M's the mass of the object and v is how fast it's moving. And the kinetic energy of rotation is 1/2 I omega squared, where omega is how fast the object is rotating in radians per second, and I is the object's moment of inertia, a thing that depends on an object's size and shape, as you'll learn by reading the book and also by doing this lab. Now when something rolls without slipping, v, the object's speed, and omega, the rate at which the object is rotating, are related. In fact, omega, the object's rotational rate, is equal to v divided by r, where r is the radius of the object. Usually, you'll see that the other way around, where the object's center moves at speed v if it rolls at angular speed omega times r. So we can build that into our conservation of energy equation. On the left-hand side, gravitational potential energy is mgh, but here we'll use delta h to reflect the fact that we don't really need the object's absolute height, we just need its height compared to how it is at the bottom of the ramp. And we have kinetic energy of translation 1/2 mv squared, and we have kinetic energy of rotation, but here omega has been substituted with v over r. So we have 1/2 I v squared over r squared. What's left now is to factor out common terms from the right-hand side. So I factored out a whole 1/2 mv squared, which leaves a 1 on the left-hand side inside the parentheses, and I over mr squared on the inside. You might have to do a couple of steps there to verify that's true. In fact, if you wanted to, you could just distribute the 1/2 mv squared back into the parentheses to see that you get the equation above. And the last thing is to solve for v, and that's fairly straightforward. Notice that m on the left-hand side of the equal side and m on the right-hand side of the equal side do divide out, but we're left with m in the denominator underneath the I. So there's the expression that will predict for you the speed of an object that rolls without slipping down a ramp. Notice that you would have to measure the height that the object rolls through vertically. You'd have to know the object's moment of inertia I, and its mass and its radius, apparently. But in the lab, we might see that that simplifies still further.